Today's lecture is on graphs and sets. First, graphs. An introduction to graphs. In this chapter, we will introduce the section on graphs, the programming definitions, give some examples where graphs are used. After this chapter, you should be able to state a few examples of applications of graphs. Okay, so we're going to go over the motivation, the terminology, representation as data structures, and implementation in C++. Okay, first of all, what's the reason for graphs? Many problems concern objects or locations that are connected with some sort of relationship. For example, airline routes. Airline routes are connections between cities and some sort of relationship between them. Perhaps price, perhaps distance, something like that. So in essence, airline routes are made up of graphs. Another example is electrical circuits, where you have different connections to different components with different features of the components. Okay, for example, we have job scheduling. We want to schedule a task to complete a job using the minimum amount of time or the minimum amount of processes. It could also be a graph. Okay, so a graph is a mathematical object that can model all these situations: airline routes of the airports and flights, electrical circuits of components and connections, and scheduling jobs, the task and the order of doing all those tasks. So now in this module, we're going to learn the definition of a graph with respect to programming and introduce the terminology of graphs. And after this module, you should be able to differentiate trees, graphs, and linked lists, and find all the cycles of a graph, as well as define and illustrate complete, sparse, and dense graphs. Now, the names for this terminology of edges and vertices actually have their origin in geometry. When you label a polyhedron, you have the sides, and then you've got these things connecting, these points at these corners, which are called vertices, and the things connecting them are called edges. So from this, we get the term vertices and edges. So as a graph, we have these vertices and we have these edges connecting the vertices. Edges are drawn as lines connecting these circles that are the vertices. Now to the topic of topological equivalence. If you look at these two pictures, they look quite different. But actually, if you look at them carefully, A is connected to B and F and C. This A is also connected to B and F and C and G, sorry. So you've got A is connected to B, G, C, and F. So this A is also connected to B, G, C, and F. So you see that they have the same connections. And if you check this for every single vertex, G is connected to A and E. This G is also connected to A and E. So although they are laid out differently, they are actually the same graph. So as long as the same vertices are connected, then they are the same graph. If there are weights on the graphs, on these vertices, then you need also the weights to be the same. Okay, so let's define some things. Simple path, connectedness, and cycles. First, what is a path? It's a list of vertices in which successive vertices are connected by an edge. So is A, F, D, E, G a path? Let's look. A, F, D, E, G. Yes, it is a path. Okay, because there's an edge between each vertex. Is B, A, D, E a path? B, A, no. There's no direct link from A to D. So it is not a path. A simple path is a path where you never repeat the same vertex. So is B, A, F, D, E a simple path? B, A, F, D, E. Well, we never repeat a vertex, so Yes. Is CABAF a simple path? CABAF. Well, you notice that we visited A twice, so it is not a simple path because of the repeat of A. A graph is connected if there exists a path from every vertex to every other vertex. So this graph here on the left, from every vertex you can get to every other vertex. This path here on the right, from this group you can't get to that group. From that group you can get to this group. So this one's connected and this one is not connected. Cycle. A cycle is a simple path in which the first and last vertex is the same. So how many unique cycles are there? Well, look, A, G, E, D, F, A. So we've gone one cycle. A, G, E, F, A. We've gone another cycle. D, E, F, D. We've gone another cycle. So there are actually 3 cycles in this graph. Permutations of the same cycle are considered the same cycle. So D, E, F, D, or E, F, D, E, or F, D, E, F, they are all the same cycle. Remember trees that we looked at previously? How many unique cycles are there in a tree? There are none. In fact, you can't have a cycle in a tree. So a tree is a connected graph that has no cycles. And remember our linked list? 1, 2, 3, 4, 5, 6. How many children? 1. Everything has only one child. A linked list is essentially a tree whose nodes have 1 or no children. Okay, completeness. Oops. A complete graph is one where there is a direct connection between every vertex. So from A, there's a direct connection to B, to C, and to D. Every vertex has a direct connection to each other. A dense graph is one where most of the edges in what would have been a complete graph are there. Most. Okay, so like this is only missing CD. A sparse graph is where most of the edges are not, most of the vertices are not connected to each other. So A and F are connected, C and G are connected, but everything else is not connected. So that's considered a sparse graph. So a complete graph has all the edges present. There's an edge from every vertex to every other vertex. A dense graph has most of the possible edges. Of the 6 possible edges, only 5, so there are, of the 6 possible edges, 5 are present in this. So most of them are there. A sparse graph is a graph with few edges compared to vertices. So there are 7 vertices, but there are only 2 edges. Spanning tree. A spanning tree is a subgraph that contains all the vertices of a graph, but just enough edges to form a tree. So an example spanning tree of this graph is this. You notice that there's exactly no cycles, right? Then we've removed enough connections, enough vertices, we have removed enough edges that there are no cycles. And is the spanning tree unique? No, it's not unique. In fact, we can think of another spanning tree for this by removing E and keeping, removing FE and keeping GE, right? That's a different spanning tree. So, question, is this a complete graph? Is this a connected graph? And what is a possible spanning tree for this graph? So please answer the question. Digraph. A graph whose edges have directions so they're like one-way streets. Whereas the previous graphs we looked at is like two-way streets. So here, every edge has a particular direction. You can go from Y to W, but not from W to Y directly. Okay, Y, there's an arrow going to W, but you can't come back this way. You have to find some other way if there is another way. As it turns out, there is no other way in this particular one, but it's possible that in another one there might be another way going around somewhere. Weighted graphs. A graph whose edges have costs associated with them are weighted graphs. So for example, here is a weighted graph where FA has a cost of 2, DF has a cost of 0, FE has a cost of 2. So where we might use them? For example, in a graph of distances between places. From Taiping to Ipoh has a cost of 1, Ipoh to KL has a cost of 3, KL to Kuantan has a cost of 5, Kuantan to Malacca has a cost of 5. So can you guess what this cost might be? Yes, they are hours. How many hours, I think, that it would take to drive. Of course, these are only approximate. So, summary of graph terminology. We have composition, which is edges and vertices. Classification, which talks about complete graphs, dense graphs, sparse graphs, connected graphs, regular graphs, digraphs, weighted graphs. And paths, simple paths, complex paths, and cycles. And the note that a tree is a connected graph with 0 cycles. Now let's look at how to represent graphs. In this module, we'll discuss graph representations as data structure. Oops, grammatical mistake. That should be as data structures. After this module, you should be able to represent a graph as an adjacency matrix, as an adjacency list, and as a set of ordered pairs. Let me just fix that grammatical mistake while I'm at it here. Okay. It's taking me a while to save this. Okay, continue. Okay, first we have representation, two-way adjacency matrix, and adjacency list. Adjacency matrix, a 2D matrix where two axes are the vertices and the intersections are the edges. So we have a matrix like this, where you go from A to B, there's a link. See, A to B, there's a link. B to A, there's also a link. And then A to G, there's a link. So you see A to G, there's a link. But A to E, there's no link, so you see there's a blank there. Now note, this is an undirected graph. There are no arrows, right? So then the matrix is symmetric. If there's a link from F to A, there is a link from A to F. So it's symmetric along the diagonal. But a digraph, you can have a link from Y to W, okay, Y to W, but you don't have a link from W to Y. W to Y, there's no link. So directed graphs, the matrices may be asymmetric. And for a weighted graph, F to A costs 2, so we put 2 in F to A. Okay? F, A, that's 2, and of course, since it's not a directed weighted graph, you can say AF is also 2. So we put the weights in the intersections, and if it's as before with a regular graph, it is symmetric, and if you have a directed graph that's weighted, then it won't be symmetric. So, how are we going to write the adjacency matrix representation of this graph? Well, let me get a pencil up. Pointer options, pen. Okay, so first we have to label the edges. Okay, let's see, 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Okay, so there's 7. So we have typing, there's Ipoh, there's Kuantan, there's KL, there's Malacca, there's Muar, and there's Singapore. Same here, typing, Ipoh, Kuantan, KL, Malacca, Muar, and Singapore. Now, from typing to typing, you don't need to take any time. So, same with everybody. So, there's zero cost. If you're at the same place, there's zero cost. Then, from Ipoh to typing, it's 1. So, it's symmetric because we are saying that this driving distance is the same either way. Then Kuala Lumpur to typing, there is no direct link, so we don't put something there. Okay? Ipoh goes from to typing as to Kuala Lumpur. So Ipoh goes to Kuala Lumpur 3. Kuala Lumpur to Ipoh 3, same. Then Kuala Lumpur to Kuantan is 5. Oh, sorry, that was Kuantan, that's not Kuala Lumpur. Oops, my mistake. Pointer option, eraser. Okay. Pointer option, pen. So, sorry, this is Ipoh to Kuantan. There is no link. Okay, Ipoh to KL, there is. It's 3. And KL to Ipoh, there is 3, right? Kuantan to KL, there is 5. Kuantan to KL is 5. And similarly, KL to Kuantan is also 5. And then Kuantan can also go to Malacca, also 5. So Kuantan goes to Malacca, also 5. And Malacca goes to Kuantan is 5. KL to Malacca is 2. So KL to Malacca is 2, and Malacca to KL is 2. Then Malacca to Muar, Malacca to Muar is 1, and Muar to Malacca is also 1. Then Muar to Singapore is 3. Muar to Singapore is 3, and Singapore to Muar is also 3. So this is the adjacency matrix representation of this graph. Then representation as adjacency list. So an adjacency list is having a list that's stored for each vertex stating the vertices to which it has an edge. So the list for this is like this. Let me change my pointer to laser pointer. So you see A has connections to F, B, C, and G. See? A, F, B, C, and G. B only connects to A, so there's only one thing there. C connects only to A, so again there's only one thing there. D goes to F and G, so D goes to F and E, F and E. So this takes less memory than a matrix if it's a sparse graph. Okay, linked list of course takes an extra pointer. So if it's a dense graph, a matrix will take less memory. But if it's a sparse graph, then a matrix takes more memory than a list. And if you have a digraph, then the list still works. See, from T it goes to W, from U it goes to T, from V it goes to T, so it works fine for a digraph. Now, if you have a weighted digraph, then you need to include a value and not just the list of vertices. So, let's write the adjacency list representation of this. Pencil, pointer options, pen. Okay, so from 1, where can we go? I can go to 2, I can go to 4. So my list should have 2 and my list should have 4. From 2, where can I go? I can go to 3. So from 2, I can go to 3. From 3, I can go to 1. So 3, I can go to 1. And from 4, I can go to 2. 4, I can go to 2. So here is my adjacency list representation of this particular directed graph. So in summary, we can represent graphs using adjacency matrix as well as adjacency list. Now for implementation. Okay, so in this module, we will use C++ to use arrays to implement graphs using adjacency matrices and linked lists to implement graphs using adjacency lists. After this module, you should be able to implement in C++ a graph using arrays and a graph using linked lists. Okay, take for example this problem. We've got roads in this village called Alor Khwarizm. And we've got several businesses. We've got Govinda Singh's Clinic, you've got Ahmad's Mini Market, Bob's Restaurant, and Afat's Auto Repair. And because in this village, there are some one-way streets, then that's why the distance is not, the time taken is not the same. It takes 2 minutes from Govinda Singh's Clinic to Ahmad's Mini Market, but it takes 3 minutes to come back, and so on. Or maybe it's kilometers. Okay? It's 2 kilometers to Ahmad Mini Market, but due to a one-way street, it takes 3 kilometers to come back to Govinda Singh's Clinic, and so on. So 5.1 kilometers to Afat's Auto Repair, and 4.9 kilometers to come back. And for Afat's Auto Repair, it's a one-way street going to Govinda Singh's Clinic, so it's only going one way, for example. Bob's Restaurant, there's a two-way street going to Afat's Auto Repair, but there's a one-way street going to Govinda Singh's Clinic. So implementation in C, well actually C++, I forgot to change that to C++, okay. It takes so long to save. Okay, implementation in C++. You can implement using two-way adjacency matrix, which means that we use a 2D array. Or we can use an adjacency list, which means we use linked lists. Okay, array style, one-dimensional array for node names. We have a one-dimensional array to remember the names of the nodes. So node 0 is Ahmad's Mini Market. Node 1 is Govinda Singh's Clinic. Node 2 is Afat's Auto Repair. And node 3 is Bob's Restaurant. So we would need a 2D array, which is a matrix for connections from Ahmad Mini Market to Ahmad Mini Market. Of course, it takes no kilometers, and to Govinda Singh's Clinic it takes 3 kilometers, and to Afat's Auto Repair it takes 5.1 kilometers, and to Bob's Restaurant there is no direct road, and so on. So here is our C++ code. We have this array, which is this array up here, 1D array for node names. Then we have this array, which is an adjacency matrix. This is two-dimensional, and it shows you exactly this data, except that I called it no path here instead of no road. Okay, so, but same thing. Then in the main, we have the user entering where they're coming from and where they want to go. And then it reads the distance from the adjacency list, or if there isn't one, it'll say there's no direct road. So when you run this program, let's say you type Bob to Arfat's, then from Bob's restaurant to Arfat's auto repair, it's 7.2 kilometers. By the way, in case you're wondering, I used rfind so that you don't have to type the whole thing, Bob's restaurant and Arfat's auto repair. All I need to do is just type the first few letters that make me distinguish between the different place names. So if you type AH, then it might get Ahmad or it may get Arfat, depending on which one comes first. I think because we had Ahmad come first, it will get Ahmad and not Arfat. But if you type Ahmad, then you get Ahmad, and if you type Arfat, you'll get Arfat. So it'll tell you that from Ahmad to Bob, there is no direct road. So what is the flow of the program? How do we find out if there's a road from place A to place B? How do we initialize the array if its contents are unknown at compile time? So what's a program flow? Well, first we set up a 1D array connecting place names to matrix index. Then we have an adjacency matrix with distances between the places. We get the origin and destination from the user and convert the user's input to a matrix index by searching through the place names array, and we read the distance from the adjacency matrix. How do we find out if a road exists from place A to place B? Well, we look at the intersection of the two in the array. If it has the no path label, then there's no road. If it has a number, then there is a road, and the distance of the road is that number. So from the source code, if roads from to is not equals to no path, then we know that there is a road from that place to that, from this place to that place. How do we initialize if its contents are unknown at compile time? Remember this one, we knew the contents at compile time, so we could just initialize the array like that. But if we don't know the contents at compile time, we could store the data as a matrix of numbers in a file, for example, like this, and then you just read the 2D array into your matrix using nested for loops. So we have discussed how to implement in C++ using two-way adjacency matrix. Now let's look at adjacency lists, which we have to implement using a linked list. So in the linked list style, this is the VP diagram for that same village that we showed you in the picture. See, from Ahmad, there's a 5.1 kilometers to go to Arfat. So you see Ahmad, 5.1 kilometers to go to Arfat. And 3 kilometers to go to Gurwinder. So Ahmad, there's 3 kilometers going to Govinda, and so on for all of these things. So let's look at the code. Here's the header of the code, first part of the header. We have defined all these place names just to make it easy for us to refer to them by their names rather than by numbers. And we also define number of places. Then the node's data is simply the name of the node. And C++ requires us to use struct when we are referring to a record that hasn't been defined yet. So you see, we noted at an earlier lecture that you don't have to use struct a lot of times, right? Like for example, here, struct road node, but here I don't have to say struct place node and struct node road. That's because struct place node has already been defined. But here, road node has not yet been defined, it's defined down here. So we need to use struct to tell it, by the way, this is a record, okay? So that's why we have to say struct. Otherwise it'll say, I don't recognize this word road node. Road node, what's road node? Because it hasn't been defined yet. But by using struct road node here, then you're telling the C++ compiler, actually this is a record. And place indicates the place that this node goes to, whereas next is our linked list structure for the next node. So here we have the places. At first we initialize it to null. Okay, so we use this array to easily have pre-initialized place nodes. In real life, you'll probably normally have to initialize it during runtime by reading from a file or getting from the user or something. And then here are the functions for creating the graph list. And this part reads the info from the graph. So the main looks very much here. We've got the index, the from index to index place name, and then here we tell it call the init roads to initialize the graph, which is this init road that we're going to have. And then we ask the user from and to. So you see it's quite similar to the earlier one, but here we have to call init roads. And this part is quite similar to the earlier one as well. And this part is also quite similar to the earlier one. And here, find road distance. This is to find the distance of the road from the place referred to by from to the place referred to by to if there's such a road. If there isn't such a road, then it returns no path. So the place referred to by from to the place referred to by to, and there. So when you run it, it looks just like this. From 3 to 2, which is from Bob's restaurant to Arfat's auto repair, it looks it up, it's 7.2 kilometers. From 0 to 3, Ahmad Mini Market to Bob's restaurant, there's no direct road. It looks like I left out a space here. So I'm just going to add the space. Oh, it's from this. All right. Every time it's safe, it takes so long. Okay. And the initialization, here we're just manually linking all the places linking from Ahmad 3 to Govinda, and then link from Ahmad 5.1 to Arfat, and linking so we're just basically going through all the arrows and putting them down. And we add a new road node from first place to second place in the linked list of roads. Here is exactly what it's doing. From and to and the distance. So the road node, it makes a new road node, it goes to the distance. The place is the to. Okay? And the road next to from road. And the road here goes to the road. So okay. So let's look at it. How do we find out if there's a road from Bob's to Arfat's? And how do we initialize the array if its contents are unknown at compile time? So how do we find out if there's a road from Bob's to Arfat's? We start at place Bob and we follow the pointer. See, we start at place Bob. We follow the pointer to the first road, to which we check and it says it goes to Govinda's. Which is not what we're looking for. We were looking for Arfat. So then we go to the next one instead. Okay, we are back at Bob's, going to the next node. And 7.2 going to Arfat, and we go, yes, that's what we were looking for. So the distance is 7.2. How do we initialize the array if its contents are unknown at compile time? Well, we'll need to use linked list functions like those in chapter 3 and create a new road node for the roads and add additional links to the destinations as we read them from the file or whatever it is you're reading from. Implementing graphs in C++. Oops, sorry. Okay, implementing graphs in C++, we have contiguous arrays or linked list style. So in a contiguous array, we have a 1D array to hold the names of the nodes. And in linked list style, we also have an array of records or linked list to hold the names of the nodes and pointer directed to the first node of that node. And then we need a 2D array to hold the information about the connections between the nodes, whereas In a linked list style, we have kind of a tree style node with 2 pointers to hold the information about the connections between the nodes. Okay, now that we've managed to set up our graphs, how do we traverse our graphs? So in this module, we'll discuss graph traversal using depth-first pre-order and depth-first post-order. After this module, you should be able to traverse a graph using both depth-first pre-order as well as depth-first post-order. Okay, depth-first pre-order traversal. The general algorithm for pre-order traversal is you have starting from a particular vertex, you check, has this vertex already been visited or not? If it hasn't, then we mark this vertex as having been visited and we do whatever processing you want to do on this vertex, and then for each vertex connected to this vertex, you recursively call the traverse graph pre-order again. So, example, we've got this graph. How do we do a pre-order traversal? Okay, we're going to assume that the edges are stored in the order of the vertices to which it's going, so that we have a specific order here. Okay, so it's going to, if you're starting from A, then it's going to go to B before it goes to C and before it goes to D. Okay, so this is B, C, D. So starting from vertex A, well, pre-order says we first process our current node. So we're processing A and we push A on the stack. Then we process B and we push B on the stack. Then at B we process F because we're at B now, right? So the node is, if we looked at A, it's already processed, so we don't do that one. We go to F and we push F on the stack. And then now we're at F. So we'll process C first because it's first before G. So we process C, put C on the stack. And C, we will go to E before we go to G. So we go to E first, we push E on the stack. And then we realize E has no unprocessed nodes connected to it. C is already processed. So we're going to pop E off the stack and go back to C and continue where it left off, which is now going to G. So we process G and we put G on the stack, and now we're left with C is already processed, so we're going to go and going to D, and D, we process D and put D on the stack, and D has H, so we go to H, process H and put H on the stack. Then we realize H has nothing else, so we're going to pop H off the stack and go back to D. And D has nothing else, so we pop D off the stack and go back to G. And G has nothing else, so we pop G off the stack and go back to C. And then C has nothing else, so we pop C off the stack and go back to F. And F has nothing else, so we pop F off the stack and go back to B. And B has nothing else, so we pop B off the stack and go back to A. And A has nothing else, so we pop A off the stack and we are done. So the pre-order traversal is A, B, F, C, E, G, D, H. So post-order, it's just like you did it with trees, right? Mm. So you mark this vertex has been visited, then for each vertex V connected to this view, traverse it, then only perform the action you want on the vertex after you've done it. So here is an illustration. Again, the assumption that the edges are stored in alphabetical order. So we go push A on the stack, and then we are not processing A yet, so you see there's no output. Then we push B on the stack, and again we're not processing B yet, so there's no output. Put F on the stack, and we're not processing F yet. Put C on the stack. Again, we're not processing C yet. And these guys are done already, so it goes to E. And E has no children, so we process E. Then we come back to C and pop the E off the stack. Then we go to G. And these two are done, so it goes here, D. D Again, we don't process yet. We go to H and we say, oh, okay, H is the last thing. So we process H, and we pop H off the stack. Then we go back to D. And this is the last thing, so process D. And then we go back to G. And this is the last thing, so we process G. And go back to C. And this is the last thing, so we process C. And go back to F. And this is the last thing, so we process F. And go back to B, which is also the last thing, so we process B. Then we go back to A, and we process everything, so we come back to A and process A. Here is the traversal. This part is the same as in graphmat.cpp. It's setting up the same graph. Then here we have the traverse graph. Okay, so we start from 0. That means everything is not visited yet. Then we traverse the graph starting from 0, and if the place has not yet been visited, then we visit it and we do our processing, which in this case just print it out. Then I go through all the places and check if there's a path, then I visit that place. So the output will be Ahmad's Mini Market, Govinda Singh's Clinic, Afat's Auto Repair, and Bob's Restaurant. So the explanation of this is that we started at Ahmad and we marked it as visited. Then we followed the first road, which is Govinda, and marked that. And only road goes back to Ahmad, so we pop. And then next road from Ahmad's Afat. And from Afat, Govinda already visited, so we pop out, go to Bob instead, and pop all the way out to finish. So now we have this is the traversal. So we need to add this additional information to tell whether we have visited it, if we are doing a linked list. And we have the same road node, and we have the same this part as before. And we have this traversal routine called. Here we have the same setup as graphlist.cpp. So for pre-order traversal, we check to see if it's not visited, then we make it visited and we output. And then we go through each road and traverse the graph. So the output's the same right here. So it's similar to the matrix version, the same algorithm, only a different structure. Oh yeah, the output may be different because it can take the roads in a different order. In the matrix program, it took the roads in the order of the index in the array. But in the linked list program, it took the roads in order of the linked list, which can be in a different order. Okay, for this quiz. List 2 ways of implementing a graph. Then name 2 ways of traversing a graph. And is traversal of a graph unique? Okay, sets. So we've done with graphs and now we're going to sets. So in this set chapter, we're going to learn the definition of a set with respect to programming and introduce the terminology of sets. Discuss set representation as data structures. Again, a data structure. It should be as data structures. After this chapter, you should be able to represent the set using linked lists as well as the set using linear bitmaps. Okay, back. Okay, sets in C++. There's only one kind of object in a set, whether in C++, okay, well, I suppose in a different language, like Python, you could have different types of objects. But in C++, your objects are just one set, one type, which is letters, numbers, records, or whatever. The order doesn't matter, and hence it's different from the ordered pairs of tuples. And an example used is Dijkstra's algorithm in chapter 10, but that's much later, so don't mind about that. Okay, linked list implementation of sets. We have a linked list with a head and tail, and to make it easy to find, we keep things in alphabetical or numerical order. And the new set makes an empty linked list, exactly the same code initialization as part of stacks and queues. Remember when we did stacks and queues last time, we had this new stack on new queue, so that's same idea. And insert element searches the list to make sure the element isn't already there before inserting. Since the list is in order, so once we find the place where it's supposed to go, we can tell. Okay. Is element searches the list to see if the element is already there or not. Since list is in order, we don't have to search the whole list. Union is to go through the two sets and creates a new set containing the elements from both sides. So it's similar to merge sort later that you'll see. And intersection goes through the two sets and creates a new set containing only elements that exist in both sides. And here's the C++ code. So we have to have these special values to mark the head and tail. Last time we used it was characters, so we used key value 0. Well, here it's integers, so we're just using these special values that we will not have real values of like this for the value, so then we can use this. So if your set is going to have values like this, then you use something else. Okay? And the linked list declarations are from here to here. And we just type def the LL node to set so that we can just refer to it as a set like that. By the way, union is a special word, a reserved word in C++, so that's why I had to say union underscore. In C, I didn't have to say union underscore. So when I converted this from C, at first I got an error there. I'm like, what's going on? And then union is a reserved word in C++. Then intersection is here, and then we have the main program to call the functions to create two sets, set A and set B, and then we inserted some elements 1, 2, 3, 4 into A and 3, 4, 5, 6 into B. And then we can create we print the sets, and then we create a union and intersection here and then we are going to check to see what's in the set and what's not in the set. Here's the new set function, which is just like your new node function last time. A new list function, the new linked list function. And here's the insert. We have to search through the set to find the place that we should insert it, since we're going by alphabetical or numerical order. And if the new element isn't already in the set, then we create a new node and insert it in there, just like in the linked list. Is element, we search through the set to see as long as whether we can find the element in the set up until the point where it's going to be obvious it's no longer there, and return the key if it is there. Return true if it's there, sorry. Okay, union. We check to see if the either list is empty. If it's empty, then it's just the other list. And we skip the head nodes, and then we copy from the first place to the last place, and then we copy the leftovers because one set may be bigger than the other set. So we copy the union of S1 and S2's value into the result, leaving S1 and S2 undisturbed. See? So we return result. See, the result is a new set. Intersection, we check to see either list is empty, and then we skip the head nodes, and then we have to check that both elements that both lists have the same element. Then we copy the S1 and S2's value into the result and return, leaving S1 and S2 undisturbed. So the output is you set 1, 2, 3, 4. Set A is 1, 2, 3, 4. Set B is 3, 4, 5, 6. 1 is in set A. 6 is not in set A. 1 is not in set B. 6 is in set B. And the union is 1, 2, 3, 4, 5, 6. The intersection is 3 and 4. Okay, so how is the uniqueness of every element in the set preserved? How does the union function work? How does the intersection function work? And are linked lists the only way to implement sets? So how is the uniqueness of every element in a set preserved? Well, we keep the list in order so we can search until we find the proper spot. Once we're at the proper spot, we see, is it the item we're looking for? If it is, then we don't add it. Okay? If it isn't, then we can add it. Or if we are looking for the item, we can say it is there or it's not there. How does the union function work? We skip down each list from start to end and see which current element is larger and put the larger one in the new list and advance the pointer. If both are the same, then we put one in the new list and advance both pointers. When we get to the tail node, we're done. So we just copy the rest of the other list. How does the intersection function work? We advance a pointer of the first set until smaller than the current item of second set. Then we do the other way. Now both S1 and S2 pointers are pointing to the same element. Then we put the element in the new list. Because intersection, we want it to be in both lists. And we repeat till the tail node. Now linked lists are not the only way to implement sets. We can use hash tables, we can use linear bitmaps, and this is great if the range is small enough to fit into our integers or our large integers. Okay, I'm going to demonstrate this for just using 1 byte. Okay, how to do the linear bitmap implementation. So the largest number, it depends on your word size. So if it's 32 bits, then you can go up to from 0 to 31. If it's 64 bits, then you can go from 0 to 63. So we're just going to do this for an 8-bit 1 byte thing. So it goes from 0 to 7. And essentially you look at the binary and you put 1 where the item is in the set. So this one shows you that I have 1, 2, and 5 in the set. And I don't have 0, 3, 4, 6, and 7. So union is very easy. You just bitwise OR. Okay? Bitwise OR. 1 or 0 is 1. 0 or 0 is 0. 0 or 1 is 1. 0 or 0 is 0. 1 or 0 is 1. 0 or 1 is 1. 0 or 0, 0, and 1 or 1 is 1. So we've got the union is 0, 2, 4, 5, and 7. So union is bitwise OR, which is in C++ is single OR bar. Intersection is bitwise AND, which in C++ is the ampersand. And insert element is shift left and OR. So the element is, you want to insert element you want to insert element I into the set A, then you shift left I, and then you shift left 1 by I, and then you add it to A, OR it with A. So what I mean is that, let's see, where's my pen? Okay. Let's say your A is this one. Oops, why did it do that? Never mind, just leave the scratch. Okay, let's say your A is this, so it's a 0, 1, 2, right? That's 2. So A is the set 2. And I want to add 4 in it. Okay, so 4 is, I shift 1 4 steps. So 0, 0, 0. This is not 2. This is 3. This is 4. 0, 1, 2, 3. This is 3. Sorry. 0, 0, 1, 2. Sorry, it's 3. It's 2. 0, 1, 2. 0, 1, 2. 4 is 0, 1, 2, 3, 4. Right? Why is it shift right 4? See, if I shift, originally 1 is 0, 0, 0, 0, 1, right here. So if I shift by 0, then I'm staying here. If I shift by 1, I'm going here. If I shift by 2, I'm going here. If I shift by 3, I'm going here. If I shift by 4, I'm going here, which is correct. So why is it doing this nonsense? This or this is 0, this or this is 0, this or this is 1, this or this is 0, this or this is 1, this or this is 0, and this or this is 0. So we have 2 and 4. Okay? So our set contains 2 and 4. So that's how this. So that's insert element. So is element is shift left and AND. So we want to check to see if this array has, this set has 4 or has 2, let's say 2. Then you shift left 1, 2. So your 1 is here, and you AND it. 0 or 0 is 0. 0 and 0 is 0. 0 and 0 is 0. 1 and 1 is 1. And the rest are 0. Okay, so this is true. Because it's not 0. Anything that's not 0 is true. So, here's the code. The main program and function prototypes are identical with the linked list version. This is possible because we simply change the type definition of set from being a linked list node pointer to an unsigned integer. Okay, unsigned integer here. Oops, I can't see my pointer because it's a white pen. Pointer, laser pointer. So it's an unsigned integer here. Then this same sample main program calls the set functions to create two sets, 1, 2, 3, 4, and 3, 4, 5, 6. Okay? This is the same set as before. And then we run it, and you get the same result because it runs the union and intersection the same way, and you will get the same result as last time. The important thing is all these bit set functions. New set is 0 because 0, 0, 0, 0 means the set is empty. Then insert element, like I said, shift left the element and OR it with the set. Is element, shift left the element and then AND it with the set. Print set, I go through is shift and its element and print it. And oops, I left this as printf. It's supposed to be cout already. It worked anyway. I guess, yeah, because printf still works in C++. And set union, OR it, set intersection, AND it. And it's much faster than the linked list as a result. So how is the uniqueness of every element in the set preserved? How does the intersection function work? And how does the union function work? So the uniqueness of every element in the set is preserved because it is determined by the corresponding bit. So the uniqueness is automatically maintained because it's either that bit is 0 or 1. It's binary, so it cannot be anything else, right? So it cannot be anything else than 0 and 1. So if the thing is there or the thing is not there, that's it. How does the intersection function work? Well, we have bitwise AND. So for each bit in the algorithm, the resulting bit is that bit and with the other bit. So that's why that's how the intersection function works. The union function is bitwise OR, so it's that bit or the other bit. Okay, so quiz. Name 3 ways to implement sets, and where might these sets be used? When can you use the linear bitmap implementation? And write C++ code for the union function for linear bitmap implementation. And also, so you're supposed to answer the questions, huh? Okay, graph summary. Sorry, this slide was not supposed to be there. I forgot to remove it. Graph summary. Yeah, why don't I remove that slide then? Actually, and then I'll remove it later. So why graphs? We have problems involving objects or locations and the connections of graphs between them, and these problems can be represented by a graph. Terminology of graphs, we have composition of vertices and edges. We have classification of graphs, which is the complete graphs, dense graphs, sparse and connected, and digraphs and weighted graphs. And we've got the different types of paths, the simple path, complex paths, and cycles. And a tree is a connected graph with 0 cycles. Representation and implementation in C plus 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 plus. I might as well delete that solution thing. Okay, representation and implementation in C++. We've got the two-way adjacency matrix, which is the 2D array, and we've got the adjacency list, which is a linked list. And we've got a full linked list implementation of this particular graph, for example. And that's it for today's lecture.